this channel. I'm finally making the video of Subtopic 6.2 Periodicity Part 2, where we will talk about electronegativity and also ionization energy. So we'll start off with electronegativity and then followed by ionization energy. Electronegativity. What is actually electronegativity? It's the ability of an electron to attract the bonding electron to itself in a covalent bond. In the other words, it's actually the ability to attract electron to go into the atom. So let's say this is my atom, and then I have one electron at the outermost shell. So I have electron out there that I want to attract this electron to go in. Okay, so that is the electronegativity. If it is easy to attract, then the electronegativity will be very high. So if it's easy to attract, then the electronegativity is high. Vice versa of it, if it is hard to attract electron, then the electronegativity will be very low. Okay? Only two things. If I'm easy to attract electron, then the electronegativity will be very high. If it's very hard to attract electron, then the electronegativity will be very low. That is the basic thing. How do I know whether it's easy to attract the electron or it's hard to attract the electron? Simple. Electronegativity will be highly affected by the size. You can see over here, I have two different sizes. Smaller atomic size, and also I have one bigger atomic size. Okay, so electronegativity will be highly affected by the size. I have a small one and a big one on the screen right now. I have my nucleus over here, and you know that your nucleus is your positive charge because the presence of proton. And then you have your presence of electron in here, and then you have your electron in here, So I have an electron out here, and the electron want to go into this outer shell. And that is my nucleus. And because the size is smaller, so logically, is that easier to attract the electron or harder when the size is smaller? Obviously, it's easier because the nucleus attraction from the nucleus to the valence shell is closer. So when it's closer, the force of attraction is stronger. Therefore, the electron from outside want to go in is easier. So when the size is smaller, the electronegativity is higher. So bear that in mind, when the size is smaller, the electronegativity is higher. Vice versa of the bigger size atom. When it's a bigger size atom, I still have my nucleus over here. Your nucleus is still holding a positive charge due to the presence of proton. And your electron is still in the shell. You still have your electron in the shell, standard. But since the size is bigger, and then you want to pull one electron go in. And since the size is bigger, what happened to the nucleus attraction from the nucleus to the valence shell? The nucleus attraction will be weaker. When the nucleus attraction is weaker, whether it's easier to pull the electron to go in or it's harder? It's harder to pull the electron to go in. Why? Because the nucleus is very far from the outermost shell. So it's harder for the electron to go into the outermost shell. Therefore, electronegativity will be lower when the atomic size is bigger. So bear that in mind, electronegativity is highly affected by the size. And when the size is smaller, electronegativity is higher. When the size is bigger, electronegativity is lower. Okay? Next, let's see what happens to the electronegativity when you are going across a period and also when you are going down a group. First and foremost, what are we going to look at when we are moving across a period or going down a group? We are going to look at the atomic size. Why? Because we know that electronegativity is highly affected by the atomic size. We are going to look at what happened to the atomic size when we are moving across a period. So, we have learned that in the part 1 video of 6.2. What would happen to the atomic size when we are moving across a period? The size of the atom when you move across a period gets smaller. So you know that over here, atomic size decrease when you move across a period. And if you remember why, it's because effective nuclear charge. And since the atomic size becomes smaller, what happened to the electronegativity? We have talked about that just now. When the size is big, the force of attraction from the nucleus to the outermost shell is very weak. And therefore, the electron out here that want to go in, that want to be attracted by the nucleus, will be very hard. Alright, it will be very hard to attract the electron to go in because the atomic size is very big. Therefore, the force of attraction from the nucleus to the valence shell is very weak. And since the electron is very hard to pull in, therefore, the electronegativity decreases. Vice versa, what happens when the size is smaller? When the size is smaller, the force of attraction over here is stronger. So when the force of attraction is stronger, what happens to the electron that want to go in into the outer shell? It's easier for the electron to go in because the nucleus and the outer shell is very close. So the force of attraction is very strong and the outer electron is very easy to be attracted into the atom. As a result, electronegativity increases. Therefore, when you move across a period, your electronegativity increases because the size of the atom decreases. Okay? And what would happen when you are going down a group? We have learned that in a previous video. You know that when you are going down a group, what happened to the size? When you're going down the group, the size from small will become bigger at the end of it. Why? Because of the shielding effect. Alright? If you don't understand this, please watch the previous video, 6.2 part 1, where we will talk about why the atomic size change when you go across a period and going down a group. So, due to the shielding effect, when you go down a group, the atomic size increase. And how does this atomic size increasing will affect the electronegativity? So when you go down a group, the size get bigger. Therefore, the electronegativity will become lower. Will decrease. Why it will decrease? Like we have just mentioned across a period just now, because when the size is bigger at the end of the group, it's very hard for the negative electron to go into the shell. Why? Because the distance is very far. When the distance is very far, the force of attraction is very weak. So when the force of attraction is very weak, it's very hard for the nucleus to pull the electron to go in. Therefore, the electronegativity decreases when you go down a group because the size increases. Alright, is that clear? Simple. And the conclusion that you can use for the electronegativity going down a group is as given. When you go down the group, we'll talk about the size first. That will relate to your part 1 6.2 video. So the size increase when you are going down a group will be affected by what? The number of shell increases. When the number of shell increases, so what happened? The shielding effect increases. When the shielding effect is very high, the force of attraction from the nucleus to the valence electron will be very weak. Therefore, the atomic size will become bigger. When the atomic size becomes bigger, it will have a weaker ability to attract electron to itself. Alright, remember that is my nucleus. If the size is very big, the electron want to go in will be extremely hard because the nucleus is very far from the outermost shell. So this force of attraction is extremely weak. So when the force of attraction is extremely weak, the electron that want to go in is very hard. Therefore, it will have a weaker ability to attract electron to itself. When the ability is very low to attract electron, therefore, the electronegativity will decrease when the size increase. So basically, it's not 100% new thing that you are learning. We are only adding a bit more to the size that you have learned previously. You have learned in your 6.2 part 1 video until here, where the atomic size increased. So what are we adding for this video is only the ability of attracting electron. So if you have a very high ability to attract electron, electronegativity will be very high. But if you have a very low ability to attract electron, then the electronegativity will be very low. So it's not really 100% a new thing. It's just something extra on top of what you have learned in your 6.2 part 1 video, or about the size that we've been talking about. Alright? Next, what happens when we are going across a period? So when you go across a period, the size again will be affected by what? When you go across a period, we'll talk about SES rules if you remember. And SES rules is affected by number of proton. So when you go across a period, the proton number increases. When the proton number increases, the effective nuclear charge increases. And when the effective nuclear charge increases, what happens to the force of attraction? The force of attraction from the nucleus to the valence electron will be stronger, and therefore the size decrease. So it means what? It means the size at the beginning is big and it becomes smaller at the end. And all that is something that you have learned in your part 1 video. Okay? If you don't remember, go through that again. And what would happen when the size decreases? What would happen to the electronegativity? When the size is smaller, is it easier to attract electron? So let's see. When the size is decreased over here, we will have a higher ability to attract electron to itself because it's closer. So the nucleus and the outermost electron is smaller. So the force of attraction is stronger. The outside electron is easier to go in. Therefore, you have a higher ability to attract electron, and as a result, you have a higher electronegativity. That's why when you are moving across a period, you will have a higher electronegativity. Higher electronegativity means what? Means it's easier to become an ion. An ion means negative charge ion. Because you are accepting electron, you attract electron to go into you, so you accept electron and you become negative charge. So when the electronegativity is high, it's actually easier to become an ion. And that's why when you go across a period, you can see I have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. And obviously, chlorine is easier to accept electron than sodium, right? We always have Cl- rather than Na- because it's easier for the chlorine to accept electron rather than the sodium. Make sense? Better? Simple. As a conclusion for electronegativity, electronegativity is actually highly affected by atomic size. Alright? Atomic size. And we know that atomic size is highly affected by shielding effect when you are going down a group. Okay, so we are still talking about the same thing. When you are going down a group, the atomic size will increase. And the next one, effective nuclear charge. And when do we use effective nuclear charge? We use effective nuclear charge when we are going across a period. Okay, and all that is because of the size of the atom, whether it's increase or decrease. So electronegativity, in a conclusion, is affected by atomic size. Atomic size is having two factors, shielding effect and also effective nuclear charge. And remember, when do we use shielding effect? When do we use effective nuclear charge? Also, a conclusion for electronegativity, when the atomic size increase or when the atomic size is very big, the electronegativity, the ability to attract electron, will decrease. Okay, when the size is very big, it's very hard for you to add in electron because the force of attraction is very weak. Vice versa of it, when the atomic size decrease, when the atomic size becomes smaller, when you have a smaller size, what happens? Your electronegativity increases because it's easier to attract electron, because when the size is smaller, the nucleus attraction to the valence shell is stronger. So when the force of attraction is stronger, the electron out there is easier to go in. So electronegativity increase. Bear that in mind, electronegativity is the ability to attract electron. If you are okay with this, then we move on to another thing. We have ionization energy. So what is actually ionization energy? Ionization energy is the minimum energy needed to remove 1 mole of electron from 1 mole of gaseous atom to form 1 mole of gaseous unipositive cation. Cation. Why cation? Because you remove electron, so you become cation. For an example, means if I have X and then I'm going to form X positive plus electron. So I'm forming a positive charge because I remove electron. Okay, so that is what I mean by ionization energy. Bear that in mind, we are talking about the word energy, not ability. Alright, we are talking about the word energy. So think about that. And what would happen if the electron is very easy to be removed? Alright, if the electron is very easy being removed, do I need a lot of energy? If you have a box and now you want to move the box and it's very easy for you to move the box, do you need a lot of energy? No. I will only require a very small amount of energy if the electron is very easy to remove. Okay? And since I only require a small amount of energy, then my ionization energy will be very low. Okay? So bear that in mind, when the electron is easy to be removed, you will only require a small amount of energy. When you only require a small amount of energy, then the ionization energy is very low. Simple. So let's look into the vice versa. What happens when the electron is very hard to remove? When it's very hard to remove the electron, okay, you will need a lot of energy. Imagine you have a box and it's very, very hard to move the box. You will require a lot of energy to move it. Okay? So when it's very hard to remove the electron, you will require a lot of energy. When you require a lot of energy, it means your ionization energy will be very high. I hope it makes sense to you that when your electron is very hard to remove, you will require a lot of energy to remove that electron because it's very hard to move it away. So you need a lot of energy to throw it out. Therefore, your ionization energy will be extremely high. Bear that in mind, we are talking about energy. Okay? Next, how do I know the electron can be easily removed or the electron require a lot of energy to remove. Like your electronegativity, ionization energy also highly affected by the size. Size of what? Your atomic size. Alright? So let's see what happens when it's big and what happens when it's small. Again, your nucleus, standard, that is your nucleus. And as always, your nucleus having proton and your proton holding positive charge. So what happened over here, different from electronegativity, is ionization energy is remove electron. We are no longer taking in electron, we are talking about removing electron. So which electron we are going to remove? We are going to remove the electron at the outermost shell, your valence electron. Okay? So we need to think whether this electron is easy or hard to remove. So let's see. That is your nucleus. So your nucleus to your electron having one thing called force of attraction. And when the atomic size is smaller, what happened to the force of attraction? The force of attraction from the nucleus to the valence electron will be stronger. When the force of attraction to the valence electron is stronger, means this electron will be strongly hold to the nucleus. And since the electron now is strongly held by the nucleus, do you think the electron is easy or hard to remove? Of course, it's very hard to remove. When the electron is very, very hard to remove, do you need a lot of energy? Of course, a lot of energy is needed. When a lot of energy is needed over here, what happened to the ionization energy? Ionization energy will increase, or the ionization energy will be very high when the atomic size is very small, because the force of attraction from the nucleus to the valence electron is very strong. Make sense? If it doesn't, let's look into what happens when the atomic size is bigger. When the atomic size is bigger, your nucleus, the same. Your nucleus will be forever having proton, and in your nucleus will be always positive charge. So, valence electron is out here, and this valence electron will experience a type of force of attraction. You will have force of attraction from the nucleus to the valence electron. And the force of attraction is weaker when the size is bigger, because the electron is very far away from the nucleus. So the force of attraction is weaker. Since the force of attraction is weaker, do you think this electron is easy to remove? Yes. Easy to remove. When it's easy to remove, do you need a lot of energy? No. Less energy needed. When less energy needed means your ionization energy over here will decrease. As a conclusion, when the atomic size is smaller, the ionization energy will be very high because the force of attraction from the nucleus to the valence electron is very strong. Therefore, the electron or the valence electron is very hard to be removed. As a result, a lot of energy required to remove the electron. So ionization energy increases. Vice versa, when the atomic size is bigger, what happened to the valence electron? The valence electron will be very far from the nucleus. When the valence electron is very far from the nucleus, the force of attraction will become very weak. When the force of attraction is very weak, then this electron is very easy to be removed. When it's very easy to be removed, then you only need a small amount of energy. Therefore, when the atomic size is bigger, ionization energy is lower. And that is how atomic size is affecting your ionization energy. Alright? And I hope you understand until here. Okay? So let's move on to how ionization energy will change when you are going across a period and also going down a group. So we know that when you are moving across a period, we know that the size becomes smaller. Alright? When you move across a period, your atomic size decreases. And we know from your previous video, this is highly affected by the effective nuclear charge and number of proton. That's why the size becomes smaller. And as what we have talked about just now, ionization energy is about remove electron. Okay? So we know that when the size is bigger, it's easier to remove electron because of the force of attraction is weaker. Therefore, less energy required. Vice versa when the size is smaller. When the size is smaller, hard to remove electron. Why is very hard to remove electron? Because the force of attraction is very strong. Since the size is very small, the nucleus is very close to the valence shell. As a result, you need more energy. So the ionization energy will increase when you move across a period because the size when you move across a period is smaller. Okay, so ionization energy increases. And what would happen when you go down a group? Okay, so when you're going down a group, everybody knows that when you're going down a group, the size will become bigger. So from small to big. And when the atomic size increases, we know that in this big size of atom, it's easier to remove electron. Why is easier to remove electron? Because the force of attraction from the nucleus to the valence electron is weaker. So when the force of attraction to the valence electron is weaker, the valence electron is not strongly hold to the nucleus. Therefore, it's very easy to remove. When it's very easy to remove, you will only need a small amount of energy. When it's only a small amount of energy, what happened to the ionization energy? So when you are going down the group and the atomic size increase, your ionization energy will decrease. So as a conclusion, when you go down a group, the ionization energy decrease, and when you go across a period, the ionization energy increase. And all this is because of the atomic size. And this is the conclusion of ionization energy when it's going down a group. When you're going down a group, what will be affecting the size? Bear in mind, when we are going down a group, we will talk about number of shell increase. When the number of shell increase, what is the factor affecting the size? Shielding effect increase. Everything in here is your part 1 of 6.2 video. Okay? And when the shielding effect increase, what happened? When the shielding effect increase, the force of attraction from nucleus to the valence electron will be weaker. Because you have more shell, the size is bigger right now due to the higher number of shell. So your shielding effect becomes stronger. Your force of attraction from the nucleus to the valence electron over here is weak. Okay, therefore the size becomes bigger. When the size is bigger, is that easier to remove the valence electron or is that harder to remove the valence electron? Since it's very far and the force of attraction is very weak, obviously it's easier to remove the electron. When it's easier to remove the electron, you will need less energy. When we only need a very small amount of energy, that's why the ionization energy decrease when you are going down a group, as the size from small to bigger. Therefore, when you're going down a group, ionization energy decrease. And like I say, it's not totally a new thing. Big part of it is about why the size is bigger. Only this last part is about ionization energy. Okay, so most of them is about the size, why the size is bigger. Next is the conclusion for ionization energy moving across a period. When you're moving across a period, what happened to the atomic size? So when you move across a period, we know that the proton number increases. Therefore, effective nuclear charge increases. When the effective nuclear charge increases, the force of attraction from the nucleus to the valence electron will be very strong. When the force of attraction from the nucleus to the valence electron is extremely strong, the atomic size will become smaller. When the atomic size becomes smaller, what happened to this electron? Is that easier to remove or harder? Of course, it will be very hard to remove. Why? Because the force of attraction from the nucleus to the valence electron is very, very strong. When it's very strong, means that the electron is tightly close to the nucleus. Therefore, it's very hard to remove. And when it's very hard to remove, I will need more energy to remove it. When I need more energy, the ionization energy increases when you are moving across a period. As a conclusion to ionization energy is the energy required to remove electron. And we have two conditions over here. If the electron is easy to remove, alright, if the electron is very easy to remove, means you only need a very small amount of energy. Therefore, ionization energy is very low. But if the electron is very hard to remove, you need a lot of energy to remove the electron. Therefore, ionization energy is very high. Okay? And how do we determine whether it's easy to remove or hard to remove? Will be 100% depends on the atomic size. Okay? Atomic size also will be again highly affected by shielding effect and also effective nuclear charge. As always, shielding effect is used when you are going down a group. And effective nuclear charge will be used when you are going across a period. Okay, so it will be very similar as your part 1 video of topic 6.2. Go and watch that, okay? And it's easy to remove means the atomic size is big. And it's hard to remove because the atomic size is very small. And everything back to the force of attraction from nucleus to the valence electron. Okay? Easy? Simple. Very simple. But we have exceptional cases, or we call anomalous cases in period 2. Anomalous cases or exceptional cases that happen in period 2 is between beryllium and boron. We have learned that just now, when we are moving across a period, the ionization energy should increase because the size gets smaller. But if you look at the chart over here, the beryllium and boron ionization energy from beryllium decrease when it's moving to boron. And according to what we have learned just now, I have lithium, and from lithium moving to beryllium, it should increase. Moving to boron, it should increase. Moving to carbon, moving to nitrogen, moving to oxygen, moving to fluorine, moving to neon, everything should increase. But if you look at the beryllium and boron, and also nitrogen and oxygen, you can obviously see that the ionization energy decreases. Why this anomalous behavior happen? Why it doesn't increase over here? Okay, we'll look into the reason. This is the SPDF notation of beryllium, 1s2, 2s2 as given. And then I have my boron, I have 1s2, 2s2, 2p1. And bear that in mind, ionization energy is about energy required to remove electron to become cation. So over here, which electron we are going to remove? We always remove the electron in the highest end or the furthest from the nucleus. So in beryllium, the one that further away from the nucleus is this electron in the 2s. While in the boron, the one that furthest away from the boron is obviously the one sitting in the 2p1, which in the orbital diagram is this electron. What do we see is beryllium having higher ionization energy. And from what we can see in the chart, boron, meanwhile, having lower ionization energy than your beryllium. So the question is, why boron having lower ionization energy? Lower ionization energy also means it's easier to remove this 2p electron. The question is, again, why is easier to remove this 2p electron? This is because 2s orbital is closer to the nucleus. Therefore, the force of attraction from nucleus to the 2s orbital is stronger. So, when the force of attraction from the nucleus to the 2s is stronger, therefore electron in 2s orbital require more energy to remove. But the 2p orbital is further away from nucleus compared to 2s. So when the 2p orbital is far away from the nucleus compared to 2s, therefore the force of attraction from nucleus to 2p orbital is weaker. When it's weaker, therefore it's easier to remove. When it's easier to remove means you need less energy. That's why your beryllium and boron, beryllium need more energy. The reason is because 2s orbital is closer to the nucleus, resulting a stronger force of attraction. Therefore, you need more energy to remove the electron. That is the reason why you have these anomalous cases in period 2 between beryllium and boron. We have another one over here. Last one. The another anomalous cases in period 2 is your nitrogen and oxygen. As we can see from the chart just now, your nitrogen also having higher ionization energy than oxygen. By right, if you are moving across a period, the ionization energy increase, oxygen should have higher ionization energy than nitrogen. But over here, obviously it didn't. Why? And this is the SPDF notation of nitrogen given. This is the SPDF notation of oxygen given. And the electron that we are going to remove in the nitrogen located in the 2p. And the electron that we are going to remove from the oxygen also located in the 2p. And is the last electron that we put in. So it's this. This is the electron that we are going to remove. And the problem over here is harder to remove or easier. And as you can see, nitrogen having a higher ionization energy in the chart. If the nitrogen is having higher ionization energy, means it's harder to remove because you need more energy. That's why the ionization energy is higher. Vice versa, oxygen in the chart having a lower ionization energy. It means this electron is easier to remove. When it's easier to remove, means it requires less energy, and that's why the ionization energy is lower. The question over here is why it works that way. Why it's harder to remove this electron in nitrogen than this electron in oxygen. Both of them are located in 2p. If you realize, both of the electron is located in the 2p. Since both are in the 2p, we cannot mention about distance because their distance will be the same from the nucleus. Both are in the 2p. And over here, the main reason is because this orbital right now having an extra stability. This orbital is what we call half-filled p orbital, or half-filled 2p orbital to be detailed. Well, this 2p orbital is just a normal partially filled orbital. So what makes the half-filled 2p orbital and also a partially 2p orbital different? Because we have one stability stated that half-filled 2p orbital is more stable than a partially filled 2p orbital. And since it's more stable in the half-filled p orbital, that's why you need more energy to remove the electron from the half-filled 2p orbital. And since it's more energy, therefore the ionization energy is higher. Slightly different from the beryllium and boron. Because in the beryllium and boron, we'll talk about the distance from the nucleus between 2s orbital and 2p orbital. But between the nitrogen and oxygen, we'll talk about the stability of the half-filled 2p orbital and the partially filled 2p orbital. So separate that. But both of these will apply similar to the anomalous behavior in the period 3, magnesium and aluminium, and phosphorus and sulfur. So for magnesium and aluminium, we'll talk about the distance between 3s orbital from nucleus and also the 3p orbital from nucleus. The same thing as in period 2. While for phosphorus and sulfur, we'll be talking about the half-filled 3p orbital and also a partially filled 3p orbital. Which one is more stable and which one need more energy to remove the electron from them. And that's it for this video. Thank you for watching this video, and if this video able to help you to understand more about electronegativity and ionization energy, do press the like button and subscribe to my channel for more video. Thank you for watching. I'll see you in the next video.
TunePocket.com